Welcome everyone, and today we're going to go through a example about solving Knapsack problem using Gurobi-Python interface. And today's objective is we're trying to see if we can, using Gurobi and Python, find out all the alternative optimal solution for the knapsack problem. Especially for the knapsack problem, a lot of times with the same objective, we can reach optimal solution, but the optimal solution may be multiple of them. And we want to see there's two techniques we are going to introduce today to see how can we, using a so-called no-good cut we're talking about in the last lecture period in the chapter 12, last page of the chapter 12, and talking about this no-good cuts. Okay, the no-good cuts basically cut off the current optimal solution and trying to find another binary solution. In that case, we can use the same concept. We can use the same concept to figure out all the so-called alternative optimal solution for knapsack problem. We're going to have introduced two different versions. One version is using this no-good cut. The other version is using the Gurobi's internal so-called solution pool search, using a solution pool and using that particular mechanism to figure out all the alternative optimal solution. So let's start with the first one. First version is very straightforward, utilize this so-called no-good cut. And this notebook is the so-called Knapsack Gurobi 1 notebook. And briefly introduce what is the so-called knapsack problem. Usually we have a maximizing a objective function subject to a knapsack constraint, which is less than equal to constraint, and each one of the items we have each one of the item we have the weight, okay, and the total weight we carry has to less than the capacity of a knapsack. But also each one of the item we carry produce a specific revenue or profit, and we want to maximize that profit. And all the decision variable x0 all the way to x8 or 0, 1 variable in that case. So they're called binary variable. So I'm going to start with a very simple version of knapsack problem formulation, and you can see that it's only one constraint, so it's not overly complicated. But the goal is not in the formulation, it's more of how we figure out the alternative optimal solution. And first we actually do is we're going to using a subroutine, or we'll call it a function called add a no-good cut. And this no-good cuts actually divided our current solution into basic and non-basic variable. Okay. So we define a similar situation we have in the our notebook. X equal to 1 equals the basic, f is equal to 0 is non-basic for now. Then I'm going to add in this constraint, which is sum of the variable in B minus sum of the variable in MB is less than equal to the length of the B minus 1. It's very similar to this no-good cut. Okay, we just move the one together using this situation. So moving items to different side of the constraint. So we will come up with this constraint as well. So the name of the constraint we call it no-good cut, and so on. And of course I give an example data right here, and I have a total of 9 of them, and the profit vector and the so-called weight vector and the capacity vector, C. Okay, so it's just very small problem. So first we create an empty Gurobi model called M, an abbreviation to M, and add decision variable, and we call it X, and X is a binary variable. And set of a objective function equals to the pi times xi for I in the range from I to 1 to n, and we're trying to maximize it. All right. Also, and the constraint, we only have one constraint, is omega transpose times x. And the constraint is omega transpose times x is less than or equal to c. And we'll call this constraint knapsack constraint. I'm going to start adding the so-called lazy constraint. Lazy constraint basically is the constraint we're going to add to the no good constraint cut portion. And we'll illustrate later on how to do that. And we update the model, okay, m.update, and setting the parameter, and the long go to the console equals to 1. So here I can decide if I want to suppress all the outcome or I want to see all the computational result. Okay. Going to restart the kernel, rerun to all the above. So model building is done, so we can run m.optimize and to get a solution. And I print out the solution, and I write the current model into output file called knapsack.lp file. And we can see that this problem solved for several iterations, and only one solution found is 29. Objective function is 29, and this is the current solution. Okay, so actually the model got solved using a pre-solve, actually, and is already got to very quick got a first best solution. So they didn't even know going through the branch and bound process. The pre-solve, the heuristic algorithm actually already find the best solution. And then we can print out the objective function and the solution for that case. And then we can also display the solution in the vector format. Okay. And next, the code below is trying to find all the alternative so-called optimal solution by adding this no-good cut. The purpose of a no-good cut is trying to eliminate the current optimal solution, see if we can find another alternative solution which have exactly the same objective function value as the current, the best lower bound we found. So that means we're going to do a while loop called search pool, and boolean is yes or no, and until if this is search boolean is equal to true, we keep doing the while loop. Otherwise, we jump out of it. First, we're going to set the search bool equal to true, the current iteration equal to 1. And my current optimal solution equals to empty set, and we do this while loop. And we're going to optimize it first. If the outcome of the first this optimization is optimal solution obtained, we're going to start doing this if statement. I'm going to print if this is a new iteration, store the current solution. If k equals to 1 in the first iteration, I'm going to store the current objective function equal to the z optimal. The z optimal is the current best known optimal solution we have. And then we, for k equals to greater than equal to 1, then we set it z new, or the new optimal, new objective function we find into the z new. We compare this z new with the z optimal. If they are the same, which means we're still the optimal solution, then we write out a solution and we adding the cut. Following, I'm adding this constraint and call this function to add one more constraint into our model. All right. And then, so this particular so-called no good constraint just cut off the current optimal solution and see if we can find the alternative one. And here we'll print out the solution we have currently and print out how much the total budget is using, which is the, and in the very beginning, how much the budget of the 20 we are using in that sense. Okay. So we're currently using omega times the solution and give me how much budget we're using out of 20. After that, we're going to save the solution into a vector called solutions. We're going to append that current solution into the end, increment the k number of iteration by 1 and reloop. Otherwise, if we find a solution is less than or inferior than the current optimal objective function known so far, we're going to print that one also and tell them, oh, okay, the last solution we found is no longer optimal. We should be stopping this. We'll set the search pooling equals to false, and then we jump out of the loop, while loop. Or possibly we can, since we're adding so many cuts, eventually we don't find any feasible solution, and then we also stop the search by setting the search pooling equals to false. And eventually we'll print out the solution and write out the current, the final models into a LP file. All right, and this is the first part, and we're going to start running this. Sorry, see if we can run this. So we run this, we get start running this, we get initially, let's restart this and restart the kernel, rerun everything again. I'm sorry, and give you better idea what's going on. Okay, so this particular portion is just helped me to find out all the alternative optimal solution. So iteration 1, we got 29 as my optimal solution. Then this is the current solution, optimal solution, and this is the amount of budget to use. This is for iteration 1. And after that, we run to iteration 2. Again, the optimal solution is still 29, okay? And this is the solution. However, the amount of budget we use instead of 18 is 20 now. We continue search for the iteration 3. Again, we find a 29 as my optimal solution, so the third solution, and using the total budget of 20 out of 20. Continue for iteration 4, the same thing. We find out the optimal solution is still 29. Use up the budget as 20 again. Iteration 5 is the same thing, okay? We keep adding cut, but the optimal solution keeps showing, alternative optimal solution continue to show up. And we print out how much amount of budget we use in that case. Until we go to the iteration 7, new iteration 6, I'm sorry. And then we find out this different solution is found, and this solution only have objective function of 27 right here. Okay, so we know this is the solution is no longer optimal anymore. It is inferior to the optimal solution, so we stop right here. And then we we find all 5 optimal feasible solutions to the objectives of 29, and we list all of them. But compare all these 5 solutions, only the first one actually showed up with budget consumption of 18 instead of 20. And the rest of 4 use up for the entire 20 knapsack capacity. So this is the one of the way we're utilizing the so-called no-good cut mentioned in chapter 12 as a part of the mechanism to find out the alternative optimal solution. And this is a very important type of objective, because many times a knapsack problem, not only we wanted to maximize my total profit, but also I want to minimize my budget consumption, which is the weight consumption. So this is one of the way to figure that one out. We're going to put on pause, and we'll come back to talk about a second method using the Gurobi's pool search method, SolutionPool search method, to figure on all the alternative optimal solution in that case. Okay, let's start with the second approach called Knapsack Gurobi-2 pool search method. We're going to utilize the so-called Gurobi's so-called SolutionPool search method. Keep all the solution into a pool, and we figured out, can we determine or find all the alternative optimal solution on him. And first we introduce this data we call the ground set, okay, equals to from 0 to 9 like we had it before. The objective coefficient, which is the profit coefficient, and the knapsack coefficient, we'll call it weight, W, to begin in the last lecture. And the budget equals to 20, the same thing. We create a dictionary between the ground set and the coefficient, and create a dictionary between the ground set and the knapsack coefficient. So we can print out the so-called profit coefficient and the knapsack coefficient. Now they are in the dictionary format. Okay, so followed by the index and then by the value. All right, so, and this part is very identical to the part we have, except 2 line. So building a model, we call the model, okay, called the pool search, and then we'll define the variable and call element, okay, called EL. And define the model is maximization. The objective function equals to element products the objective coefficient dictionary. Okay, so it's basically x transpose times the coefficient of a dictionary. I show you a different way to calculate the objective function, so this is basically the same. Okay, model constraint, adding a knapsack budget constraint basically is the element products of the knapsack coefficient dictionary as less than or equal to the budget itself, which is 20 in our example. And the next 2 lines are different, and we're utilizing a so-called pool SolutionPool mechanism in Gurobi. We call the set parameter, and the parameters are called pool solutions. I'm going to keep a 1024. 1024 is 1024 total solution possible. Keep it in here. And set a so-called pool gap, which means how much is the gap we accepted to enter the solution pool as the optimal solution deteriorate, which means if we know from the previous example the optimal objective function value is 29, and how much 29 minus certain gap, we accept it as the same solution. Okay, so here I set a pretty small 0.01 in that case. And sometimes I know the second best is 27. If you set this gap equal to 27, and then the solution pool will accept the objective function value of 27 as part of the pool. Okay, so here we're going to semantic search for k-best solution. In that case, we're going to using the mode 2, which is going to set it for number of solution, and write out this so-called pool solution LP problem into a constraint, into a LP model. So I'm going to run all the way up to this. So we got it. Parameter equals to, I'm going to keep as much as 1024. And the gap equals to 0.01. Search mode equals to 2. You can, referring to the set parameter, pull search mode menu to see which one is the one you want. Okay, here what I'm doing, the rest of them, I'm going to hand it to Gurobi model. We're going to try this optimization. And the optimization, if the flag equals to 1, and then we're going to set the parameters, and then we're going to see if the status equals to the infeasible or unbounded, or infeasible or unbounded, and then the model cannot be solved because it's infeasible, and then we're going to exit out. If the status returned by the solver is optimal, then so we find a optimal solution, at least one, and we'll stop with the status of optimal solution. Then we're going to print the best selected. So first is the best, print the best solution. So here we printed the solution for all the elements is greater than 0.9, which is, we're only printing out the x equal to 1 portion. And then we print out the budget, how much budget they use. This portion, we're trying to see how many alternative optimal solution we found. So the model does solution count and give me the number of solution found based on the criteria we put in, which is what? Keeping 1024 is the gap is 0.01, and solution mode equals to 2. So see how many alternative solution we found. And for each one of a solution, we're going to print out their objective function value, and then we're going to using a loop to print out for each one set of a solution, what is their objective function value and the solution value, and use the budget as well. So we can list them all together. And the last two are the exceptional code. If we come up with unbounded or infeasible, we're going to print in the error message. So this last part is fairly, looks like long, but it's just a whole bunch of if, and to determine the return status for this solution process is either optimal or is infeasible or unbounded, and how I handle the error message. And the rest of them is just first print out the one best solution, Gurobi-Python, and then based on the number of solution Gurobi-Python in the solution pool, I'm going to print them out one by one, okay? Print the solution one by one, and then print out the amount of budget used based on the current solution. So we can run this portion. It's fairly quick. Okay, and here my computer using I have a 10 core, 20 logical processor, up to 20 thread altogether to solve this. Actually, we solve it and adding a cover cut, a strong cover cut, and 2 of those, and then we find out. And actually, the process takes explore 31 node using a branch and bound, solve it less than 200ths of a second. Okay, and then we find out solution count equals to 5, all of them equals to 29, with a solution no better than 0.1. And below that, and we just print out first, okay, the number of solution found, okay, and the best solution and amount of budget used is 18. Number of solution found, total 5, all have 29 as the optimal solution objective function value. And we're going to print, next we're going to print all, using a for loop, print all the 5 solution. And these are the elements equals to 1, okay, x equal to 1, element 0, element 1, element 2, element 3 equals to 1. The next solution is element 0, element 1, element 2, element 6, element 8 equals to 1, by using budget of 20 in that case. Okay, so I have 5 alternative optimal solution. They're using various budget amount. And this concludes, and this is another way to find out the so-called alternative solution. I want you to learn both ways because the solution pool is a powerful tool using by the Gurobi, and not only in the knapsack problem. Knapsack problem is one of the things easier. We have alternative optimal solution. However, other type of binaries like a facility location, set covering problem, traveling salesman problem, they all might have a so-called alternative optimal solution because the data actually given may be very close and they're not drastically different. And then you end up with a whole bunch of alternative optimal solution. How can you using this technique called SolutionPool in the Gurobi built-in to figure out the alternative optimal solution? And this is one of the tutorial given by Gurobi website as a demo, as opposed to using the binary so-called no-good cut introduced by chapter 12. And later on in chapter 6, we're talking about computational complexity. We're going back to chapter 6, and also they mentioned this as a part of a so-called model reduction or model transformation type of technique using this no-good cut. All right, I'm going to conclude this lecture for today, and we'll see you in the next lecture on chapter 6 of our textbook. Bye-bye.